Okay, now we're starting to get some answers. What we've done is we've made a larger coil similar to the one we were using in the previous video. Have a little zoom in there. Okay, so our primary wires are here and our two secondary wires are going through this load. Wound the same way. There is 3,600 turns around the core wire. So the two thick ones are the core wire, and this little thinner wire is wrapped around it just as before. So virtually the same as our previous setup, however vastly different results. Here we have a normal case of induction where when we add a load to the secondary it reflects on the primary and increases the current through the primary. Alright, so we're going to switch it on. We're at 4% duty cycle at the moment, 13 kilohertz. No problem there. We look at our digital multimeter here, says we're reading nothing because of the many turns. Like I said, over 3,000 turns of wire around that primary core wire, so we don't have much going on. If we look at the scope, so once again our yellow is showing us the voltage across the cap, the blue is across our input CSR, and our purple trace, which looks nearly dark blue through the camera, is across our 1 ohm load resistor, and at the moment I have the potentiometer turned right down, or right up should I say, so we've got about 1001 ohms across that coil. We do see the current flowing through, even though the average is 0, it's flicking between 0 and 1 milliamp. Now here's the drama. What I'm going to do now is turn up our load pot like we did before, and we'll watch the current. Now before, nothing changed on our digital multimeter. Now we've gone from just below 1 milliamp to 19 milliamps. So I'll turn our pot back up again and we'll have a look, see what happens on the scope. Okay, so we're looking at the blue trace. Last time the blue trace did not change at all when we put a load across the coil. Now I'm going to increase that load by decreasing the resistance, and we can see that the blue trace is going up and up and up and up. Oh, that was a bit far, wasn't it? So our blue trace has gone, I'm not sure what it was before, I'll turn it back down and increase the value again. Okay, so it's saying 3.26 milliamps average, because we only have the one pulse in the screen. So as we turn our load up, and up and up, you can see that our average is now gone up to about 58.1 milliamps as per that one trace we're looking at, that one pulse we're looking at. So not so good anymore. Now we're going to have a look at what the difference is between this new coil other than its physical size. So it's a little bit bigger, or it's a lot bigger, and has more turns. That shouldn't make a difference. The only difference is if we look at the original one, you will remember I say I cut a piece out of the core, and that has made the difference. There was talk about the scope ground affecting it. We can disconnect that scope ground. Go back up to our scope here. I'll once again decrease the resistance across the secondary, and you can see that our current rises and falls with the increase and decrease of the load on the primary, on the secondary, sorry. Now here's what we're going to do. Turn the signal generator off. I will not touch anything else. I'm going to swap this coil out for the other one, which as you can see is the same configuration. All we're missing is the bit cut out of the core. We'll put our new one back in here, or our original one. So I will leave the scope off for the time being. Go back up here and we'll have a look at the multimeter first. Turn our U-Butte thing back on. Now because there's less turns, there's less resistance in the primary, we do draw more current. 19 milliamps. I will turn the load up. Still 19 milliamps. We have a look at the scope. Turn the load back up, and nothing changes. So what we'll do now is we'll hook the scope back on, because we know that has no real effects because of the common ground. Okay, so once again we look at our scope. We'll decrease the resistance across the load. And there you go. Decrease the load across the secondary, increase the load across the secondary. So the only difference, other than physical size, between these two is this one here has a piece cut out of the toroid, which does not allow the magnetic flux to do one complete turn. There must be a start and an end. So that is quite interesting and well worth taking note of. So as you can see with this, as you have seen with this coil, clearly when we place a load on the secondary, it affects the primary. With this coil here, as we place a load on the secondary, it has absolutely no effect on the primary. And as I said, that is the only difference. This has a chunk cut out of the toroid core so as the magnetic flux cannot continue in a single loop. The loop is now open, and what we'll be now getting is a north and a south. So What we're going to do next is sacrifice this toroid core. I'll unwind a couple of winds and I'll cut a piece out of it. We'll put this back in, and in the next video we'll see if that made any difference at all. So far it is telling me that if we cut that piece out, the effect should be the same as this one here. So interesting stuff. No reaction on the primary from the secondary when there's a piece missing. Standard transformer action without that piece missing. We'll see you next video once I've got that all cut and rewound and back on the test bed.